Hello everyone, I'm Sanggan Kim, a PhD student of Texas A&M University. So in this video, I'll talk about instruction set architecture of y86 sequential processor. I'll focus on the format of instructions we will implement using the logistic. Let's get started. So after you watch this video, so you are familiar with instruction format of y86 ISA, and then you will understand computations of each instruction in each stage. And then finally, you will have a transformed computation table for each stage.
As far as instruction format, there are 13 instructions in total, and it is variable length instruction. So different instruction may have different size. So for example, no op instruction has just 1 byte. So small box here is 4 bits, and since it has 4 bits, it is 1 byte. And for RR move queue instruction, it has 2 bytes, and for IR move queue instruction it has 1, 2, and 8 bytes for V, so it is 10 bytes in total, and so forth. But the most important information in this instruction format is the first byte, because it has an instruction code to identify what it is, and then function code, what exactly function this instruction will execute. So some instruction has multiple options for function code. So let me clear this annotation and then annotate again. So for example, RR move queue instruction has instruction code 2, but the function code is always 0, so which means there is only one function or one thing to operate. There is only one thing to function. But however, the OPQ instruction has one OP code, instruction code, but there are multiple function code. So what are the function code for OP code? You can find that in this table. So there are 4 different function code from 0, 1, 2 to 3. So then this function code identifies what this instruction will exactly do at runtime. And here, jump instruction, JXX dash instruction has instruction code 7, but there are multiple options for function code. So you can see all the options here. So it has actually 7 different functions for jump instruction. And also C move instruction, push Q, pop Q instruction. Oh, sorry, not push and pop Q instruction. The C move instruction has a function code. So then there are 38 different combinations of I code and function code. As you studied in the lecture for data path, we organize y86 sequential processor into 6 stages: fetch, decode, execute, memory, write back, and PC update. So we will follow these stages to implement our processor. So here we have a table with computations for RM move queue instruction and MR move queue instruction, and I believe you have practiced these computations on the data path figure on the right. Like data comes from the instruction memory and then propagated to the next stages and so forth. So we will actually implement these computations for our processor. So let's review one instruction execution with these computations. So let's select RMMoveQ instruction, for example. And in general, what this instruction does is writing a value of register A to the memory. Its address, start address is RB plus D. So we can rewrite this part like this way. So we are going to read register value of RA and then write it to the memory, and its start address is RB plus D. D is displacement and RB is base address. Yeah, so this instruction is not complete, so actually the computations are listed in this table. So let's take a look at one by one. So let me erase all the inks, then annotate again. So in the first stage, fetch stage, we read 1 byte here, 1 byte from the memory, and its start address is PC, and then we store it into I-code and iFun. So each I-code and iFun has 4 bits long, and then we read one next byte from the memory, and its start address is PC plus 1, and then we store them in RB and RA, and RA and RB are 4 bits long. And then we store next 8 bytes from the, we read next 8 bytes from the memory, and its start address is PC plus 2, and we store this written data to val_c. And then next we store PC plus 10 to val_p, and actually PC plus 10 is the next address of the next instruction. Why? Because the RMMoveQ instruction is 10 byte long instruction, right? So that's why we add 10 to the PC. And then this val_p is the one of the candidate pieces which we'll select in the PC update stage. Okay, let's move to the next stage, decode stage. Since this is again RMMoveQ instruction, so we are going to read value of RA and then put it to the val_c, and then we are going to read value of RB, which is base address, and then we put it to the val_p. Then let's move to execute stage. Since in the execute stage, we need to compute effective address. So effective address of memory we are going to write. What is that? So which is RB plus D, which is effective address of the memory address. So then where are they? So where this RB and RD stored? It is stored in val_b and val_c. So as you can see in the decode stage, we stored R value of RB in val_b, and we stored D, which is displacement, in the val_c here in the fetch stage. So then we can compute val_b plus val_c, and then the effective address will be stored in val_e, output of execute. Then let's move to the next stage, memory stage. and then we are going to write the value of RA, which stored in val A, to the memory. Each address, start address is val E, effective address. We already calculated effective address in val E. Then how many bytes we are going to write? 8 bytes, because the size of register is 8 bytes. Okay, we are done for memory. And then next stage is write back stage. But since RMMoveQ instruction does not write any data to the register, there's nothing to do with write back stage, right? Okay, so nothing. So let's move to PC update. So RMMoveQ instruction does not change PC value. It's not jump instruction. So we just execute next instruction. So then where is the address of the next instruction? It is stored in, we already stored that in the PC val P in fetch stage. So we just select val P for the next PC. I recommend you to review computations for all the instructions. So you can find all the tables in figure 4.18, 19, 20, 21, and problem 4.17 in the Bryant book, chapter 4. Furthermore, I recommend you to transform tables you revisited before in the previous slides to the table on the right hand side in this slides. So what is difference between the left and right? So the in the left table, so rows are stages and columns are instructions, but a table on the right, there are instructions in row, and the stages are in the columns. Why it is necessary is it will be very useful for you to focus on one stage with all the instructions, because on the table on the right hand side, it has all the stages, but it does not have all the instructions. But the tables on the right hand side, so it has all the instructions, one stage. So because we will implement stage by stage, so we just need one stage but all instructions. So that's why it will be very useful. But you can just when you study or revisit this table to get familiar with all the computations, you can transform this table to the left to the right. Okay, this is just example. Let's just transform two instructions, RMMoveQ and MRMoveQ. So then this is the table for fetch instruction, and then we have 4 computations each in RMMoveQ and MRMoveQ. This is all about fetch computations for fetch. Then in the decoding stage, we have another table which contains only computations for decode, but it has all the instructions. So we have 2 computations and 1 computation for RMMoveQ and MRMoveQ respectively. And next, execution stage. So for MR and RMMoveQ instruction has same execution or same computation, because both instruction have to compute effective address by doing val B plus val C. In the memory stage, And for RM move Q instruction, we write value of RA or val A to the memory, and its address is val E. And how many bytes we write? 8 bytes. And then for MR move Q instruction, we read 8 bytes of memory data, and its address, start address is val E, and we write this written data to the val M. And in the write back stage, there's nothing to do with RM move Q instruction, because it is just writing the value of register to the memory. But for MR move Q instruction, we need to write the val M, which is written value from the memory in the previous stage, to the register of RA. And for PC update stage, so since both RM and MR move Q instruction does not change PC value, so we will select val P value for the next PC value, because val P has a address like PC plus 10. Okay, that's it for this video. And in this video, I talked about instruction format of y86, and then we actually went over all the computations for RM move instruction, and then I recommend you to practice all these computations for all the instruction, and then transform the tables for the computations into different form, so that we can see all the computations for all the instruction in a single stage. And in the next video, I'm going to show you the Logisim memory file generation with y02 mem script. Thank you.